First I want to start a little bit telling you about the background of VVVV or VVVV or before we say often the only important thing about spelling VVVV is that you actually, if you write it down, you should just write it like this. Otherwise Google and everybody else will not find you. But bear with me if I don't say VVVV here all the time, I'm just saying 4V or something like that. That's not so important for us. Anyway, so the background basically goes back to 1998 something, and it started not as an academic project, so we basically just met and rented space together and tried to do some things, maybe art, maybe commercial stuff. And we just wanted to do things with computer hardware at that time, and at that particular time it was really exciting that things like all these 3D graphic cards appeared in really cheap PCs at that time, which means that you could do all that stuff which has been done only before on expensive silicon graphics machines. You can do actually on your own personal computer. The other thing, the most amazing thing was that no so-called multimedia platform at that point actually allowed you to use that powerful graphic card in your computer. So we were thinking about doing something on our own. We started with that not as an idea of doing it as a commercial tool. We kind of were annoyed with the state of media art at that point, because we were thinking media art at that point is merely transforming some strange input into some strange output by means of some opaque process. So we're kind of don't want to add any more media art to that kind of system, but more kind of improving the process in between of transforming the things and allow other people to do media art other than really do that our own anymore. So although we are neither academic, neither a commercial thing, neither artists at that point, of course we had all the implications you would need to do that. We wanted to find things out in a scientific way. We want to have things really get done, and we really want to explore new things at that point, 1998. Really important thing was making things accessible at that point. And this little bit complicated preface to my talk should explain a little bit more why I'm here and how I'm here. Actually, I basically co-founded this VVVV development in 1998 and co-founded also at that time a company called MESO, which after all these years led a little bit to the situation that the main VVVV development is now done by Yorick and Sebastian Oschatz in Berlin. Two really nice guys who do all the programming at that point together with the community, and MESO basically as a power user of V4, so we do use V4 in all of our projects, and we're completely happy that many people all over the world also use VVV for all kinds of interesting stuff. We have a little strange licensing thing, which is also kind of goes into the same intermediate thing here. We're not an open source project, but you can download the software basically free from our webpage. There is no copy protection, no download, no demos, no cracks, nothing. You can just basically download. The only thing is that we trust our users that if they really use VVVV for commercial stuff, and we know it's possible, and you can really do some amazing work for the clients with VVVV, then you would need to pay us this license cost for each CPU. And it kind of works in a little bit, so we get a little tiny money for helping people, students, to do their diploma thesis with us and get some more, get some little development project funded with that. Because we're not academically funded, we don't get money from anywhere, just from the users who trust us in that way. So that's a little bit strange situation. There's a webpage called vvvv.org. It has a really nice, friendly community, so everybody who is there feels kind of good, because there are many friendly people telling how to start with the software. I have to admit, the software is a little bit difficult to kind of start with. We are still lacking a lot of documentation, which might be the reason why it's not so popular, especially in universities. Although we hope we can improve that, and I hope perhaps with this conference I can also find some more people who are kind of willing to work with us together, improving VVVV in the future. We did our first big user meeting last year called the Node Festival. We're going to do one more in 2010. and I think it will be a great opportunity for all the community to meet again. The webpage has a couple of features. I don't want to go into detail there. Basically, I want to jump over to the section where I can explain something more how VVVV works or what are the key features of VVVV. First thing, and this is I guess the most important thing, is you can program while your program is running. So we had this already with PD and Max, of course, and this extremely powerful thing. Basically, I think there's no reason why the computer or the program you're doing actually should stop. It should just run. Typically, if you do something like in Java, whatever, you do something, you have an idea to do something, then you need to wait, you need to compile, you need to upload, you perhaps need to go back to the place where you left the program and you encounter the last error, then you kind of go back into your editor, do something, whatever. So you have this strange cycle of doing things, which obviously has some historical reason why it's there. But at this point, I will not see any reason why this is still the case. To explain a little bit more why this is important, I will show a couple of photographs I took from our archives at the company. Basically, what we are doing often is doing kind of installations on site. Like we have this trade fair set up, and there are two of our programmers here trying to find a bug with some hardware which is only available on that site. So these programmers are just sitting there in some really inconvenient situation and trying to figure out certain kind of things. Or he's kind of have seen this huge screen for the first time, needs to figure out certain kind of issues with that screen. So the programmers actually often sit in kind of inconvenient places or need to help some other guys kind of debugging some really bizarre setups for doing some things, and it's kind of invaluable tool if you actually be able to change your programs, change your test strategies, or being able to hook up something for easy debugging directly on the site. Also, a big issue is, for example, games. Here are some kernels we did for MIDI, which have been shown at the Detroit Motor Show, for example, which basically need to be played in real time, and while you're playing them, actually get ideas and need to tweak the software. So here also another example of an inconvenient programming situation where you like to have the best possible tools. This is another project we did for George Michael, actually during his 25 years tour. I think this was also going to the US. And he had that huge stage here, full made of LEDs, and this all was controlled by the VVVV. And that kind of installation, you get the immediate attention of like several hundred people during the rehearsals alone if you ever stop your software. So you better leave your software running from the day you arrive at that, and better not stop it until you leave, basically. And that's what we basically did. So we developed all the content we did for that during the rehearsals while our software was running. Here's another example we did for Mercedes at the Frankfurt Motor Show last year, which was also kind of similar setup with a huge LED wall, another LED wall here behind which was transparent, and another high definition LED wall. And this is also another project basically where VVVV was extremely important to kind of prototype that whole situation, because you never basically before you actually went into that building have the opportunity to set this whole stuff up, because it's so ridiculously expensive to do that kind of stuff. You basically do not have any rehearsal time for doing that. So you need to kind of do the simulation beforehand and then start refining that on the site and then keep it running for the whole show. So here's some more images. I basically skipped all the videos because I kind of thought 40 minutes is kind of short time. So that was the point program while the program is running. The next thing is the data flow thing, the causality without language, which I think is an also quite important thing. This leads back to the idea of wires to actually connect things. Wires basically connected to the history of electricity, and so I wanted to present here the grandfather of graphical programming, Mr. Galvani, who did not really understood how this whole thing would work, but he actually was the first to kind of connect two completely independent things by a wire, and he discovered there's something happening in there. From that point, of course, the history of electricity already showed a wonderful, beautiful diagrams. I guess this is, nearly 100 years old. I don't know, 80 years old perhaps, with all the tubes. in there from some early radio receivers. So you see here with these really old diagrams that the history of graphical programming language and also the visual language of all these diagrams here has a lot to tell. And I think even though VVVV has kind of some steps made in that direction, I think there's still a long way to go up until we get diagrams of that beauty and complexity again in graphical programming languages these days. Another thing here, the kind of the predecessor of the IBM personal computer by Hermann Hollerith in 1921, also here had this wonderful graphical programming language console here, where you basically can, with wires, connect kind of which adding routine should lead to which printing or sorting routine, whatever, which was actually kind of the only way to program computers before Mr. van Neumann had a better idea. But until that, you had these really nice plug boards where you can basically patch your stuff and then have these little wonderful things here, and you can then insert them into the computer and let the computers run your programs here. You get a really nice library. So of course, analog synthesizers have been the popular culture way of doing the same thing. And yeah, here we are. This is the basic metaphor of VVVV. I think it's kind of similar to the stuff you've seen before. It's kind of similar to the stuff you still have when trying to connect a DJ mixer or something. The only advantage basically here in VVVV, which is obviously, I have to admit, the same advantage as it is in Max and VD as well. But the inputs are always on the top and the outputs are always on the bottom. So it's kind of different situation than here, where everything is basically on the back and you have to pull everything in front. So it's much easier than doing the stuff in the real world. I want to show just one little example, which is perhaps not surprising for you anymore here. This is how the interface works. I basically can connect here these things, for example, and then I connect the position of the mouse to the square and many other objects which I could use for this example. Kind of using the audio input, and I'm not sure if I have a microphone in any way. So here it's the same situation as before. I perhaps do not need to continue. So basically data is data, you connect everything to everything. That's kind of the same concept here. Okay, so this one? No. All right. The third point I want to make is, which is, I guess, another big advantage of graphical programming languages, which has not been focused on so far, is that naming things is optional, which I think is a kind of interesting topic for all people trying to teach programming. Let me show an example. If you do want something, if you want people to draw something like this V or vowel, you perhaps would start finding a couple of parameters for drawing that vowel, and then let the student kind of figure out the way of how to draw that actually. Like for example here, I have a simple, I think it's Java example, how they would do that. And this is how another student would do that. This is how a third student would do that. And basically the outcome of the program is always the same. The only issue is that maybe this student here has introduced a couple of different variables to kind of store intermediate results and have named them. This student actually has named them incorrectly, which perhaps some of you have already pointed out. But actually this kind of naming intermediate thing is something which obviously can help reduce redundancy in programming. It can help reduce error, but it can also help create errors. Here's another example of how to do that if you don't use any intermediary names. You just write down everything, but then you introduce the redundancy, which means you can get all kinds of strange errors. So in a visual programming language, you can basically do the same thing like this. I would not say it's obviously more simple, but I want to point out that it's, well, actually you need to do the same stuff, so it's kind of the same number of objects like here. But you don't need to name all these intermediary temporary results. You just connect them, and as soon as you connected them, it's immediately clear where they're coming from and where they're going to. And there's not so much this the issue that you would create any kind of redundancy or kind of wrong naming, which leads you to strange things. Another wonderful thing here with graphical programming languages, for example, here, this function here, which replaces the sine and the cosine functions here in one thing, basically can have really, really easily functions that return two results, which is, I guess, another legacy from the classical programming language, which were basically dating back to the tail typewriter, that basically you have just one sequence of events, so it's completely difficult to have something which returns several things. So you have only, you can have functions which have several parameters, but you cannot so easily have functions which return several parameters at the same time. In graphical programming, that's not a problem at all. But back to the naming. Naming things is optional. They're great, obviously, for interfacing, but obviously they're not great if the names are not meaning anything, and especially in an educational context for the students who do not know what they actually will do at first. There's a high probability that the names are not perfect at all and maybe lead only to misunderstandings. So here's another example of one artist which I was proud to work with a lot, called DirectX-shaders, and he did all kind of really wonderful animated shapes. I'm sorry I have no video here or no real-time version of this here. But he derived a lot of wonderful shapes, and it's really unclear to me how these things could ever be named, or how the parameters you use for creating these things could ever be named. It's just about the visual outcome, and I think that's a big advantage. So, that's number 3. I have to say I have 9 points to say. This is number 4 already. This is something more technical, which kind of explains a little bit of difference between PD and Max versus VVVV. In VVVV, in Max, as you have seen before, you were explained that there are messages which are pushed down the graph. So this was like similar to the example we've seen before. Basically, in Max, you kind of have data here, and data pushes messages and events down the graph. And before it's kind of reversed, you basically want to have the answer to the question of whether this thing should be on or off. And from that point on, you traverse the graph upwards, and at that point, get the result by going upwards and asking all the nodes upstream how this is going to work. The big advantage of that is that if you want to do a really smooth 60 frames per second animation and have everything run really, really, really smoothly, you don't want to have many generators here on top which asynchronously generate any changes. You basically want to make sure that every time a new frame gets rendered, you will have a correct set of data. This basically is also a consequence of the idea that we wanted to use VVVV more for graphical things. So from the beginning, it was meant to be a toolkit for high quality, like something like broadcast quality visual output. So this was one of the main architectural consequences of that idea. We wanted to do it in like this way. Another thing is that the timing itself is much more simpler as you would have to do it in PD or Max, because everything in there is happening at the same time. I think in the PD presentation there was a wonderful patch which showed something really, really simple with a lot of different messages going on, and I was kind of really happy that we do not have to do it like this way. So it was really simple. I will show another example what is possible that way. Is another little thing here. What we do have is we have these little nodes here called oscillators and dampers, and they will make really smooth animations out of any data. So here's the mouse button data I have. Then I have this node called oscillator, and the oscillator basically just transfers this thing, like the mouse button, which goes from 0 to 1, to some continuously smooth changing value here, and then uses that as the scaling for the thing. I have something similar here, but the only thing I wanted to explain is here, with this little amount of nodes, you already get a really, really smooth and elegant feeling animation, and other things want the other core features of before. So, next topic is spreads. Spreads were also one of the really first features we introduced back in '98 because we were kind of extremely excited about the idea of graphic cards at that point, which allowed you at the first time to really go into particle systems and having many objects doing interesting things at the same time. Which led us to the idea that almost all pins basically would take not just one data, they take an array of data. And this is basically for everything. I can show another example here at that point. So basically, here I have a line object which I connect to a renderer, and the line object at that point generates just one line. So that's basically a kind of simple thing. But now I have here these couple of operations, for example here, and this generates me not generates me one value, it generates me 72 values. And if I put these 72 values into that, I will get 72 different lines. I can continue that and kind of make really simple animations with many objects just by connecting very little objects here. And so I connect all these things here together and really get a smooth animation. If I want to have more or less of them, I can just increase here the numbers or decrease them again. It's all really simple and intuitive. We had this idea that one dimension should be enough for everybody, so you have basically this list of data. It's just a certain number of individual entries. At one point we stopped at the idea that this could also be binary trees or two-dimensional, three-dimensional arrays, whatever. We were kind of thinking like in the spirit of contouring, like that basically it's enough to have one dimension, everything else the user can develop on its own. So that's a simple idea. The spreads basically have only this one dimension. This makes things quite easy. So next topic is we do not want to introduce any arrows. And first thing is the point about syntax errors, which has been raised a couple of times today. The computer is there while the program gets written. This somehow reminds me of Rye's little introduction yesterday, where he played to the auto harp the idea the keyboard is there, use the keyboard. And so I would chime into that and say the computer is there, the computer is there, and the computer is there while your program gets written. So there's no need to treat the computer as a typewriter while you type the program. So first thing with graphical programming language is kind of simple to kind of avoid all kind of syntax errors, because values will connect only to values. There's no possibility to do that. The computer will just disallow that to do that. Also, inputs will always only connect to outputs, and vice versa to that. The other thing with the graphical programming language is we have no brackets, no curly brackets, no square brackets, no single, double quotes, no commas and semicolons. We have just these boxes, and we just have the connection between these boxes. So that's incredibly valuable for a teacher in that whole thing, because the interface is really simple. So the next strategy we applied a lot is wrapping. Also in the idea of kind of reducing errors. Like for example here, you have this switch. This switch can change between 3 different colors at that point. So the question is, of course, if I put in a 0 as a programmer, I would get this one. If I put in a 1, I would get this one. If I put in a 2, I would get that one. The question is, what happens if I put in a 3? And this obviously should be completely possible. Everybody should have the right to put in a 3 or a 4 or whatever, or minus 20 or something in here. So what do? Basically, we wrap this over. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. And the other crazy thing and quite helpful thing is that if you put in a -1, it's just the last, -2, -3, -4, -5, -6, etc. It also accepts floating point numbers, so there's no distinction between floating point numbers, integers, booleans. It's just the same type. It's all floating point. And the wonderful thing about the wrapping is actually that it's not really popular in programming languages. On the other side, it's really popular in all kind of our culture. Like here, the Arabic numerical system, like here in this machine, like Blaise Pascal illustrated. All kind of ornaments use all kind of wrapping. Of course, the music has all kind of wrapping chords. Also in rhythms, obviously, you have always this wrapping around the 16 things. Wonderful 8-bit cool microcomputers also have all kind of wrapping. They just wrap over the address ranges. So it's a really rich legacy, a cultural legacy of things which wrap over. And I don't know, it's not really happening in other programming languages so much. Next thing is the spread wrapping. This is also something which is different as in other languages. Like for example, if you have this question here, 1 plus 2 is 3, that's kind of simple. You can extend this also kind of simple to little vectors. Like if you have these two element vectors here, you get, okay, first plus first is 4, second plus second is 6. That's kind of simple. You can extend this to multiplication, it's also clear. The question, what happens if like you do something like this? I'm not sure how many programming languages will not show an error at that point. What V4 does actually, it returns the result and it calculates the result as follows. It basically takes the shorter element and repeats it until it fills up the larger ones. And this is also something which we are kind of happy with it, because it allows all kind of things which are actually useful. Like here, for example, which I could imagine can be helpful in calculating some kind of mathematical formula. Or here, this kind of thing which could be helpful in some kind of uniform scale operations, whatever. But at the same time, the beauty is there are no errors anywhere, and students can just do what they want and just could basically mess up everything in any way they want. I can show this here in this example. For here again, if I reduce the number here of the elements a little bit, that is a little bit. I have here a pin for the color. Basically, if I have, for now, every line has the same color, but I could put, for example, here this spread of 2 colors in there, which means that the colors are alternating between 2. So there's one here, one there. And this is vector here. Have even more colors in here, and make even more patterns here, for example. So that's a kind of easy way of doing ornamental stuff in all kind of ways. Because these spreads are all compatible and it doesn't care anybody if I have like here 8 elements connected with 65 elements. Or for example, I could disconnect it here and have only 5 coming here from that point. The others from that point. So that's all really, really simple, and you can play around with it a lot. There's a special case if there's an empty set here, which we can always an empty set. Interesting thing, where are the loops? Which I want to reply, who need actually loops? I think obviously loops are an important part of every computer science curriculum, but I'm not really sure if anybody actually needs loops. At the beginning, it was kind of a joke that we do not have any loops in our programming language itself, but after all these years, I'm kind of never really felt the urge of having one, and as soon as we had one, we just had introduced a new node which basically fulfills the need where we have this loop. Because with these kind of spreads, you can get all kind of operations already there, and if you I think at some point, obviously, the elegance approaches the elegance of using SQL for accessing data. But it's possible and it works somehow kind of well, and I'm kind of used to it at this point. So, next thing is this feature called boy grouping, like being able to have many things in sync or many actors in sync. I want to show also a couple of projects which we did, which kind of led to this idea of boy grouping. Here first, this was a club, the Kuhn Club in Frankfurt, which was like 3 years ago, which is a big space which kind of surrounded by this membrane wall, which is being projected on by 21 projectors. So we have 21,000 pixels all over around this thing. And this whole thing is controlled by VVVV. And so we have these 21 projectors and the 21 computers providing the graphic for these things. Here's another example where we had a globe, which is being projected here in this test setup only by 5, but later on by 6 projectors. Like here you see this Antarctica projector with a mirror going upwards. Here's one of the 4 projectors mounted around the equator. Also in this situation we have 6 computers kind of transforming the image to kind of project on this sphere. This has been a smaller variant with a semi-sphere, like 4 projectors below going to mirrors in the semi-circle and projecting the globe image. This is another thing we did in 2003 for the soccer championship in Germany. There's also a 360-degree projection, where on these 360 degrees all kind of different games and little information terminals put into seemingly kind of constantly evolving 360-degree animation. Here you see the projector setup. There are 10 projectors here projecting the images. So going back to this border ring thing, the idea is actually that you basically sit only on the server, and basically these clients or these boys here, they just do everything depending on how you do that. So basically you have like here, you have these 5 robots here, and you basically can say, okay, I want to have the position of the hand basically as a function of the number of the person. So person number 0 has his hand here, so the person 1 is here, so I can just calculate basically where they should land, and of course if they start dancing, everything will be in sync anyway. So that's basically the idea here, and it's done in a surprisingly simple way in the graphical programming language, and perhaps that's one of the reasons why this concept is not so popular, because it's basically so invisible in this whole language that you barely see it at all. Basically I have this patch, and I could now just select the number of nodes here and press Control V, and then these things are part of the boy group, which means that in this toolkit example, I have now 21 computers here, which basically have these 3 nodes automatically created on their machine. And I have a network setup automatically done, which basically transmits all the stuff which is going over these 2 wires over the network to these 21 computers. The wonderful thing is, I can now maybe debate that it's not really cool to kind of have these output here of this oscillator, which basically means that every 60th of a second I need to transmit 2 floating point values over the network to 21 computers. It's not so efficient, so I basically press Control V again and move that thing also to the client, which that means that I would only, in the case somebody would press the mouse, I would just then transmit the data over the network. So I have a nice flexibility here. What parts should run where to get the most out of the inefficiencies of a network, basically. So I can basically decide where to put what. Or, for example, if I basically don't want to control this whole thing with this 1 mouse on the server, but with the 21 mice on all of the 21 computers, I just select this one and press Control V again, which means that now also the mouse node is on these clients again, which means that now you can control this with the 21 mice on the 21 computers. So that's the idea about boy grouping. It's actually really simple, but it helped a lot for doing these kind of big installations actually. So next thing is we have a kind of huge library with simple and high-level nodes already. So which have a lot of all these 3-letter protocols, some more which are really helpful for controlling professional MED matrices and DMX equipment like ArtNet, ENet, whatever. We have MIDI, RS-232, HID devices are possible in the next release. And we have lots of 2D, 3D math stuff, logic stuff like flip-flops, monoflops, finite state automator. We have lots of string operations, XML operations like XPath and XSLT. Image analysis is a big issue, so many people have contributed stuff which uses OpenCV, so you can do all kind of fiducial tracking and stuff like that very easily in VVVV. You can calculate with colors. Color is a primary data type before, so you can basically directly use colors as for multiply colors, add colors, whatever. We have a lot of mesh operations to generate meshes. You can access SQL databases. You can have access to sound. One user contributed a wonderful library for accessing the bass library for playing back all kind of sound. You can access the file system, all kind of Windows specific or PC specific stuff. The next strategy we have is we're trying to embrace as much as possible open standards. So one thing is you can directly drop a free frame DLL onto the VVVV patch and directly use this free frame code to kind of process your images. A similar way you can directly drag DST plugins onto the VVVV and use them for audio processing. And since last year we have the possibility of creating your own nodes in C#, .NET environment, and so it's really, really simple to create your own nodes. While VVVV, unfortunately, or thank God, is not multi-platform, just once on one kind of well understood but strange platform like Windows, which is of course a huge advantage because it can be really fast in implementing things, but you do not have all these cross-platform issues. But we decided to have the plugin specification at least multi-platform and open source. So if you want to do plugins under Linux, you can develop them using Mono. I think there is no reasonable host under Linux at that point, but this might change. So last thing is the DirectX and shader functions. This was also one important thing from the beginning, that we want to use the shading things. And what one thing was we wanted to popularize is this HLSL shading language, which I'm not sure whoever heard of you about this. Actually, it's a really, really simple graphic. It's a really, really simple language, much like Java. But the important thing, it runs directly on your graphic card. So it does not need the CPU, it runs on the graphic card, which means that it's insanely much faster. So, for example, if you program a pixel shader, you have a program that can create subroutines which will run like 10 million times a second without any impact on your system at all. So this is something which is really a couple of orders of magnitude better than doing things on your CPU. I want to show this in one last example. So I have here basically, this is basically the same stuff you've seen already. Just want to make it a little smaller here. So this is the important stuff. This is the output. So this is basically the stuff you've seen already. There's this patch which generates here this screen saver like stuff. And here, basically I'm taking that stuff, putting it through this shader, and I'm getting this one here. This is basically the result which is coming out here. And the wonderful thing here with shaders is I can just do a right click and I will get a little processing like window actually, which allows me to directly go into this code here. And the amazing thing is I can actually immediately put something in here and it will instantly happen. So I could just put something in here or whatever, like this. So if there's a syntax error, it does not work. But so here, for example, I instantly made the image negative. And this whole thing is running on the graphic card of this laptop, so it's not the best possible performance, but it will run really, really, really fast, typically. So this is this pixel shader. Basically, you can go directly in there. Another wonderful thing is, so for example, if I want to do something I could, for example, here put a parameter called tweak in here. I could just do something like this, which perhaps not so sensible. But as soon as I basically enter this one here in the code, you will see there's here a little new node, here a parameter called tweak, which I then put here access, and basically use that for any time that I want. So I could, for example, I'm going to pour something, connect that to the tweak parameters, and now it's around here. So basically, it's really, really simple to go here to the graphic card, tap into the potential of the graphic card, and do all kinds of things. And yeah, because it's all quite accessible. Yeah, the vertex shader is another thing that I think I'm basically run out of time, so I could remove that. And, yeah, thank you very much.